Hi boys, I hope you are going to appreciate hearing my voice today for a change. So we're going to talk today about elastic potential energy, the energy stored in a spring when it's been stretched or it's being compressed. Okay, so that's the subject of what we're doing today. Hopefully you've been okay in the first two units. If not, then do send me an email. I can always set up a Teams meeting with you. Okay, so we've done the first two, looked at Hooke's law, and now we're looking at the energy stored. Right, we'll look at the work done in stretching a spring, and just want to refer to what we did earlier in an early unit, and we looked at a formula for work done by a force. And just pause the video for a second to see if you can remember what that rule was, and just jot it down. Okay, so hopefully you remember that. It's work done is the force applied multiplied by the distance the particle has moved. Now if we were to represent that in some sort of graph, so this first one here, you've got a constant force being applied to move an object. So the work done is the force multiplied by the distance moved, and you can probably work out that if you, let's say you want to work out the force applied at a certain distance to move there, represented by that green line, then really what you're doing in effect is you're finding the area under the line, area under the curve. Okay, very similar to what you did in the kinematic stuff when we talked about area under a graph was a distance moved. Similar sort of concept here. This of course is when you've got a constant force being applied. Sometimes the force is not constant, sometimes the force increases over time or decreases. Let's have a look at this one here. So this is a force increasing steadily at a constant rate. So gradually increasing the force, so the distance is moving. And again, if you wanted to work out what the distance moved would be, you could do it by finding the area under that line, okay, in a similar way. Okay, so the area of the triangle. Okay, so the work done is the area under the line. So how can we apply this formula in the context of stretching a spring? Okay, you might want to just pause the video perhaps for a minute and just have a quick think about that. Okay, so in this context, of course, if you apply a certain force to a spring, then that is going to lead to a certain extension. It's not as if it's going to apply the same force, it's going to gradually extend more and more and more. It's going to lead to a constant extension. So to get a bigger extension or a smaller extension, you're going to apply a bigger or a smaller force, more and more tension. Okay, so slightly different to the previous example. Right. So the graph is going to look more like that, where the tension, the force being applied basically, is going to gradually increase. But the same principle applies. Okay, so if you want to find the work done, you've got to find the area under the graph. Okay, so if you want to find the work done for a particular extension there, represented by that green line, then you need to find the area under that curve, under the graph. Okay, right, so the area under the graph is what gives you the work done in stretching the spring. Right, that's the basic principle here. You might want to just pause the video now and just write that down as notes in your book. All right, so let's formalize this. Okay, so we're going to look at the elastic potential energy stored in an elastic string or the spring. So we looked at work done. Work done and the elastic potential energy are the same thing. Okay, another way of doing it, another way of calling it the same thing. So the work done is stretching a spring is the area under a force extension graph. So here we are, here's a force extension graph. Okay, so you've got the applied force T on the vertical axis, so that's lambda x over L at a particular point, and the extension on the horizontal axis x. Okay, so if we're going to find the work done, then we're going to find the area under the triangle. So the area equals, tell you what, I'll pause the video at that point. You have a go, see if you can just work out the expression it is. Okay. Alright, so hopefully what you did is this. So area of a triangle is half base times height. So the half times the base, which is x, times the height, which is lambda x over L. So that gives us lambda x squared over 2L. So that is the formula for work done. Okay, so if you haven't got that written down, then just pause the video and just write that down. I'll give it to you formally in a second anyway. Okay, so we could also find the area in a traditional way by integrating, as you've done in normal A-level part of the course. Just need to make sure we understand what the equation of this line is. So the equation of this line is that T equals lambda x over L. Okay, that's what the equation of the line is in terms of T and x. So what we're going to do then is we're going to integrate that. So it's the integral of lambda x over L. We're going to apply some limits. So the limit is 0 up to this point here. Well, that's just x. Call that x. Okay. So that's 0 up to x. Okay. So if we integrate that, we're going to get lambda x squared over 2L. Okay, so add 1 to the index and divide by that power. Put the square brackets in, put the limits there, 0 and x. And then if we just substitute in that x, we're simply going to get lambda x squared over 2L minus 0. That's just going to be 0. Okay, but you can see we've got the same thing either way around. Lambda x squared over 2L. Okay. Now one thing you need to know is that the work done, as before, is measured in joules. Okay, so work done is measured in joules. Alright, so therefore we've got this formula. Elastic potential energy, EPE for short, stored in spring is lambda x squared over 2L. And that is, in other words, the energy needed to stretch a spring from where it is naturally to its extended length. Or it could be compressed from a certain point to a certain other point. Okay, same thing applies. Right, if you haven't got that down yet, then just pause the video and just copy that down for your notes. Okay, so we're just going to look at 2 examples. These examples are in the textbook actually. Okay, just a quick note there that this lambda x squared over 2L, another way of saying that is that's the potential energy in the stretched position or in the compressed position. So here's an example. So this is, like I say, just taking the textbook, so if you want to see more detail then do look at the notes. What you might want to do though is just have a look through this and see if you can work it out by yourself before you look at any notes or before I go through it with you. So just pause the video, see if you can have a go. Okay, so in this question then, we've got an elastic string, has a natural length of 1.4 meters and a modulus of elasticity of 6 newtons. You've got to find the energy stored in the spring, so the elastic potential energy this is, when the length is 1.6 meters. So what have we got? We've got a natural length of 1.4 meters, so that's our L equals 1.4 meters. Whoops. Modulus of elasticity, so that's a lambda, equals 6 newtons. And its length is 1.6 meters. That means that the extension is therefore going to be 0.2 meters. All right. So the energy stored in other words, that's the elastic potential energy. So the formula, which we've just looked at, is equal to lambda x squared over 2L. Sorry, my handwriting is not great there. Sorry, rushed it a bit. So just put the numbers in. That's going to be 6 multiplied by 0.2 squared over 2 times 1.4. Stick it in a calculator. You can have a go at that if you like and pause the video. Okay, what you should get is 0.086 joules. Two significant figures. Right, and I've got no G involved here. Okay, so you could do more significant figures if you wanted to, but 2 is fine, 0.086. Okay, good. If you haven't got that down yet, then just pause it and copy it down as notes. Right, let's move on then. Next. Right, so in this example, you've got a spring, or a string, sorry, being compressed. So it starts off at 0.6 meters naturally, and then it's compressed to 0.5 meters, and then compressed to 0.3 meters. You've got a modulus of elasticity of 10 newtons. What you've got to do is work out the work done to compress it from 0.5 to 0.3. What I suggest you do is just pause the video, have a go at it now, and come back in a second. Right, so let's just write down what we've got. We've got that the natural length, so that's L, is 0.6. And the modulus of elasticity, lambda, is 10. Okay. We could have extension 1. Okay, so that's when it's at 0.5 meters. So the extension, in fact the compression in this case, is 0.1 meters. And we could have the compression at the second place, where it's compressed at 0.3, would be 0.3 meters. Okay. So what we're going to do is work out the work done to compress it from 0.1 to 0.3. There's going to be more elastic potential energy at the 0.3 length than at the 0.1 length. So we're going to do lambda x2 squared over 2L. So that's the elastic potential energy at 0.3 meters minus lambda x1 squared over 2L. Okay, so that's the elastic potential energy when the string is 0.3 minus the elastic potential energy when the string is 0.5. Okay, so that's going to be 10 times 0.3 squared all over 2 times 0.6 minus 10 times 0.1 squared all over 2 times 0.6, and that simply comes to 2 over 3 joules. Okay. Right, so if you want to just think about that for a bit, if you're not sure about it, and just pause and just reflect on it a bit, copy down the notes. You can look at more detailed working out in the textbook if you want to, if you're not sure. Okay, if you're happy, then just let's move on. This is what I want you to do. So we're going to do exercise 3C. It's not a very big exercise, it's quite short. And then if you could do all the questions, but 6 and 7, if you could make sure that you submit that to me, please, with neat diagrams, clear working out. The stuff you've done so far has been great, so well done. If you want to have a go at that, then I'll look forward to seeing it. Okay, bye for now.